Hello sir. This is my video recording for my course project on BDA. My topic was house price prediction using geospatial data. So basically, we'll start with loading all our libraries. Dash and Dash Bootstrap components are for the real-time Dash interface, and these are the model libraries that we're importing, and some few more libraries imported. Then we initialize our Spark session, have named it our housing data analytics. Then this is the data set that I'll be using. I searched various geospatial data, but the only ones that were available online were the California-based ones. So I have longitude, latitude, the housing median age, total rooms. So basically, what happens is that inside this grid lock of longitude and latitude, all the combined housing median age, the combined total number of rooms in that grid lock of longitude and latitude, total number of bedrooms in that grid, the population of that grid, households, number of people in the household, median income, median house value. This is the target. These are parameters. This is the target variable, median house value, and ocean proximity. So all these various things, as you can see, we have all of these are numerical features, and this is a categorical data. So first we load the data in our variable, and then we print for few values, the top 20 values of the data set to see if it is working. Then we do some feature engineering. These are two basic of features to actually be able to predict any get any valuable information from them. So we do some feature engineering. So I introduced three new variables: rooms per household, bedrooms per room. By bedrooms per room, I mean number of bedrooms uh, in a total given number of house. And then we have population per household. So we have this. Uh, we have three more variables. Then we are going to convert this categorical data into numerical data using one-hot encoding. Simple indexer, apply one-hot encoding. We create a pipeline and we transform the data. Here we have this. So this ocean proximity becomes is divided into three parts: ocean inland, near bay, and near ocean. So it's 3, 2, and 1. So as you can see, like here it is. And extract each binary column from the array. We have these four variables inside this column, and we give them each a numerical data, and then we cast them into an integer type so that the model will treat them as integers. Then we define the list of numerical columns, and then we are going to try to find which are the outliers. So we use IQR method, intra-quartile range method. So the upper between like first quartile and third quartile, only the data in between is to be considered. So that the reason is we do this is because if we have too many outliers in our data set, the data becomes skewed. The model is not able to predict too well because outliers obviously they tend to pull the model towards themselves, and the predicted values will be not a true reflection of actual values. So here, like we can see like the median house value 450,000, 350, 500,000. This is the maximum the value it takes in the data set. I'll show you that in ahead. Then we are going to find out what should be our target parameters, like what should be what column should be in we should be considering for better price analysis. So then we create a heat map of all correlation map basically with the median house price with all the other features. So as you can see, median income and total number of rooms is the biggest. They have the highest correlation with median house price. So we do that, and we can only do this by converting the Spark data frame into the Pandas data frame because all these Matplot libraries and Seaborn libraries they work very conveniently on Pandas framework rather than Spark frameworks. And then we'll simply do some more data cleaning. We drop rows with any null value because there are very few rows such. So if we drop them, it doesn't really matter. And then we simple create a vector of it, and then we use standard scaler because we want to scale the values. Otherwise, the data is unnecessarily skewed. And then we split the data into 80/20, train data and test data. Simply we randomly split them, and then I'll be using a gradient boost trees model. I've tried with various models: XGBoost, Random Forest, a Light GBM. Then I even dabbled in little bit in CNNs. But the best accuracy that I was able to found was through gradient boost trees. And then we use grid search CV to see which parameters would be best suited for my model. And then we set our label, we set our the target variable and the rest of these parameters. Our metric will be RMSE, and then we use a cross validator map. We use this, and then we print these. These are our best parameters: def, bins, iterations, and then we simply find the RMSE. And then well, this is a uh, geographical visualization of our data set. So if we basically zoom in, so we can see that we have, like, for the San Francisco one, the price, the more it gets towards the warmer side, the higher the price. So as you can see, obviously, the Bay Area of San Francisco has the highest concentration of the most expensive houses. So if we zoom in, so they are, you can see, like, this in this gridlock region of San Francisco, we can see that there are, like, the median house value is around $500,000, and there are 6,000 rooms in this area, the latitude, longitude, all of these things. If we zoom out, we can see, you know, how the price varies. This is for San Diego, and see, the entire state of California is covered. We have San Francisco over here, we have a little bit of Los Angeles over here, and then we don't have any for Baja California, but yeah. Another one is this Folium library. They have very beautiful color maps, and we can easily see. So basically, the size of the circle is the price. How many uh, houses is covered in that gridlock. So basically, we use it because it provides a very beautiful satellite view, so better indicator, and yeah, we can easily see, right? All these little different shapes of how they vary. And then, so basically, we want to find out what are these the maximum values in all these particular labels. Because the way my real-time dash works is that I use sliding features. So if I open this website, takes me here. So basically, my this is a real-time web-based dashboard. So the maximum slider would be the upper limit of these sliders is the upper limit of the actual data set, these values. So I've simply, imported them in here. So the maximum value, is of this, and now I'll take you. No, so basically, what I have done for this real-time dash is I've used ngrok. So it's a free web-based service where I can simply create, I can generate my API key here, like this authentication token, and like this is one of my currently agents that are working, and my authentication keys. Yeah, this is my credential, so this cannot be changed, and this is I have to create a new key every session. So as you can see, I created this here, and this key is here, and so I have sliders. I can predict the house price based on these four parameters, and then I can obviously add tons of various parameters, but these are the most easiest and common for if anyone wants to search, but prices, and transform the data. I simply call the data in my app function here, app.callback, and then I print this. So I'll show you how this works. So like if I want to change, like let's say in my grid log, the total number of rooms is like around 6,000 rooms, and the total bedrooms are like 1,000, and the population is like 5,000 population. Number of households would be like 500. So, or maybe, yeah, that's 500 good. So like the house price it predicts is like 221. So I can see that. And if I like want to change it, I can take it even further to see if it's just not for, certain values. I can take it beyond, and then, app price, you can see it changed to 357K. And even works for it, it takes the maximum value, with the maximum column of that particular parameter variable. So we can see that. Yeah. So I've also integrated this real-time uh, graph in my dashboard as well, and then I can show you the price distribution of how the frequency count and the median house value, how it varies. So as you can see, obviously, the median house around 170, 165-ish, little bit leaning towards the cheaper side is has the highest frequency, and then we have an outlier of 500K. There are around 1,000 variables values houses with median house value in between above 5K, 500K. So this is obviously an outlier. If we remove these, then our model predicts very well. RMSE is around 20,000. But if I include this 500,000 one, my RMSE jumps up uh, like more than two times, it becomes 500,000. So currently here, I haven't removed these outlier values. I haven't like this data set. This new data set that I have is outliers underscore IQR underscore DF. But the entire of my rest of my data, I use the original DF variable that I've called, right? Like this train data, the train data was done on data prepared, the original data, right? DF here. So that's why my RMSE is slightly higher here. Otherwise, I could have simply removed those data, and my RSA would have dropped down to 22,000. And then this is the price trend of how median house value and total number of rooms varies. We can see this is a OLS trend line, the ordinary square, least square line. How this varies, we have the equation of how it varies. The R square value is very low, 0.017, which is pretty good. And how this varies, we can see that. And we can easily see like the density, right? The density of this above the OLS is very high. And yeah, so basically that's how it is. And this is my this is my PDF, my report. So currently, I can simply start it with what's my problem statement, step-by-step approach of how I've done it, and this is the correlation heat map, modeling hyperparameters, how I've done that, visualization. So these are how each parameters vary with each other. So like there are like 8 parameters. So I've like took each parameters and varied how it works with respect to each other, various different plots. And as a part of my EDA process, and this is the uh, geographical map of my dataset. And then I've described how my dash web works, the key various predict house price function, uh, three graphs, the slider feature, dynamic price prediction, and the results and conclusion, and the future works possible on this. So yeah, thank you for listening to my presentation, sir, and I hope you enjoyed my presentation. Thank you.